Okay, folks, let's dive into doing some of the math. I think you're going to like these. I mean, maybe not like them, but I think you're going to be a little more like, hey, these aren't so bad compared to some of the stuff that we have been doing this semester in terms of math. These calculations for heat changes, they're not that bad. I know you're saying, well, you're just saying that because you think everything's easy. You're teaching. No, I think you're going to find that these aren't too bad. Okay, now a quick review from the last video. I did a lot of babbling there about some theory and background. But if we had an element carbon, okay, which state of carbon would get a heat of formation value in a chart of 0? What do you mean different kinds of carbon? Well, sure, there are different kinds of carbon. You know that. Deep down inside you do. Graphite, what you use, what's in pencils. Lead's not in pencils, okay? It's graphite. So graphite is a form of carbon. Diamond is a form of carbon as well. So that's carbon. That's what it is. That's what a diamond is, just carbon. So when you have those two different forms of carbon, graphite and diamond, which one is the form that's going to form under standard conditions? Which one is going to be the standard condition form of carbon? Now, if you know anything about diamonds, you know that ain't it, because that takes a lot of pressure and temperature over many years to create a diamond. That ain't standard. So at room temperature, carbon is going to be room temperature, room conditions, atmospheric conditions, one atmosphere. Carbon, C, graphite, is going to get a 0 HF, and diamond is going to get some other value for that, whatever that might be. You can go ahead and look it up. Go ahead, do it. Okay, no, okay, fine. Okay, just a quick review. Then these are arbitrary values. Again, we just want to know the heat of reaction. So we want to know the change of the values when we have products and reactions. So let's dive in and do some of this math. All right, now, we gave you the equation in the last video. I'll put it back up again for you, though. But let's go ahead and look at number 2. It says, calculate the heats of combustion. Now, combustion is a kind of reaction. So we want to know the heat of the reaction, the change in the heat of the reaction for whatever this one is here. It's a combustion reaction, but that's just a kind of reaction. So the combustion reaction, we're going to take the sum of, remember my E-ish looking thing, that means the sum of the heats of formation of the products minus the sum of the heats of formation of the reactants. So I'll put P for products and R for reactants. All right, well, what is this reaction here? What do we have? We have some C2H4 plus some O2 plus 2 CO2s plus 2 waters. Now, we have to be careful here because I'm going to put water with the L. That's liquid water because it could be vapor, water vapor. So we have to be careful because we have to make sure we're looking up the correct state of that element or compound that we're using because under different states, they have different values. So the heat of formation of liquid water is not the same as the heat of formation of water vapor. So be careful with that. All right, carbon dioxide's a gas. That's our gas. And each one of these does have the state of matter. Of course, this is room temperature. And it does say here, if we look at standard following reactions from standard enthalpies of formation. So we're looking at standard conditions. And under standard conditions, we have some. We can do a little bit of fun Lewis structure with this. That would be what is called ethane, but we have 2 less, which means I must have a double bond in here. If I have my double bond, then I have 1, 2, 3, 4, 1, 2, 3. I'm just doing some Lewis structure fun with this compound. That's ethene. That's ethene, not ethane, because it has 2 less hydrogens. Okay, a little bit of chemistry there for organic chemistry, but it's fun. I love organic chemistry. You probably know. I just move on. Okay, I'm going. Relax. Okay, so here is the reaction, and what I want to do is take the products and subtract the reactants, and I need to know the H values for those. So I would look those up in a HF, heat of formation, chart for each one of the following. But don't you worry, you people have had a rough week, so I did the looking up for you. Who's here for you? Yeah, this guy. Okay. So I've done that. So we have, under here I put the delta HF, kilojoules per mole of 3 out of these 4. Well, why didn't you give it to us for all of them? Are you going to make us up one of them? You did. Why couldn't you just finish them all? Well, because I only had to look up 3 out of 4. But there are 4 of them. I know, but the thing is, this one, at this point, we should now know, under standard conditions, that oxygen gas has a value of heat of formation of what? 0. Yes, very good. And don't believe me, I'm not a person you should be trusting. Look it up yourself, find it. I don't mind them. Okay, well then just trust me then. Okay, trust me. So this is a 0. So I don't have to worry about the heat of formation of the oxygen because it's been assigned that 0 value. But these are not zeros, those are compounds. Those I would have to look up. Well, I've already done that for you. So let's go ahead and do this. So the change in the heat of the reaction is going to be equal to the sum of the products. Now here I have 2. This is important. I have 2 carbon dioxides and 2 liquid waters which are formed. That matters because these are given in kilojoules per mole. And we all remember that the coefficients tell me how many moles that I have. So I have 2 moles of that, so I'm going to have to multiply by 2. So I'm going to multiply the carbon dioxide value, which if we look, carbon dioxide is negative 393.5, negative 393.5, and I have 2 of them. And then I have to add add the other product, which is 2 waters. Water liquid is negative 285. Negative 285.8. Okay. Now I'm going to actually square bracket this whole thing off to remind me that I've got to do this math here first. And then I'm going to subtract. Okay, because remember we have to subtract the heats of formation of the reactants. Well, in this case, there's only one reactant that has a heat of formation because we don't have one for this. It's a 0, that oxygen. Okay, so I look up my ethene, and that is a positive 52.3. There's only one of them here, so I'm not going to multiply that value by anything, just one. So 52.3 minus 52.3. So we're going to do the math here first, get a value, and then subtract 52.3, and that'll give me my delta H of this combustion reaction. All right, so you can go ahead and do that out. It's not difficult math, just stay organized. 2 times this, get a negative value, add 2 times that, get another big negative value. Add those together, get a big negative value, and then additionally subtract 52.3. If you do that math, you should come out with, okay, go ahead, do it, I'll wait. You won't. Oh, you are doing it. Okay, good. Oh, good. All right. Do that, and you should come out with a value of negative 1411, negative 1411, and this is in kilojoules per mole. Okay, let's look at this in the answer and hope it makes some sense to us. Negative. What does that mean? It means exothermic. This reaction, the heat of the reaction, gives me a negative value as an exothermic reaction. And it's 1,411 kilojoules. That's over 1 million. That's 1.4 million joules per 1 mole of this when it combusts. Now we know that these are hydrocarbons. Hydrocarbons combust, they give off a lot of heat. That's why we combust them. So that is a lot of heat given off by a hydrocarbon in this reaction. So that answer should make sense to us. Okay, we get a big negative exothermic reaction burning a hydrocarbon. All right, so that is that first problem. We'll go ahead and set up the next one for you. All right, so the next one, this is B. We've got some H2S, gas, that's hydrogen sulfide, plus once again, we're burning it, so it's a combustion reaction. And not a hydrocarbon combustion, but it is a combustion. We have a combustion reaction here. And we're going to form some more water, liquid water, and some sulfur dioxide. All right, so sulfur dioxide gas, and I have once again put down the stuff that dreams are made of in this reaction. Okay, so let's go ahead, set this up. Delta H of the reaction equals the sum of the products. So I'm not going to put the sum of up here again because I know it's going to be the sum of. I'm going to take these two products, add them together. But remember, don't forget these coefficients. You're going to multiply those coefficients. So we've got the water vapor, sorry, not the water vapor, liquid water which is produced. Liquid water was given in the last problem. We gave that as negative 285.8, negative 285.8, negative 285.8. So 2 times that plus 2 sulfur dioxides. All right, sulfur dioxide is given here as negative 20.15. Not a big number, negative 20.15, but there are 2 of them. All right, now this whole thing gets added. That's the sum of my products. We'll subtract the sum of the reactants. Now this one, once again, goes away. It's given a 0 value because it's the common state of oxygen under standard conditions. So it gets a 0 as a result of that. So here I have 2 hydrogen sulfides. Oh, wait, did I put the wrong tone? Oh, wait, I did. Oh, did you catch it? Did you catch it? Did you? Good for you, good for you. Were you going, oh my God, I made a mistake. Yeah, I did. I made a mistake here because, see, I didn't have that coffee this morning. I should have. 2 sulfur dioxide gases. I need 2 sulfur dioxide gases. I put the wrong value in. And the sulfur dioxide gas is negative 296.4. Woo! I would have gotten away with it too, wasn't you meddling kids? Scooby-Doo. All right, now we subtract the value that I had here, because that should be a reactant. So subtract the hydrogen sulfide, and the hydrogen sulfide, just making sure that I'm not screwing this up again. Hydrogen sulfide is negative 20.15. Okay, and there are 2 of them. So 2 negative 20.15s, and that's 0. So that's the only thing on this side. So minus that. Okay, do the math. You got 2 of those and 2 of those. That gives me a negative 5 something and like a negative 5 something, and I get a negative 1,000 something, and then I subtract a negative here, so we got to be careful of that one. Last time we just did subtract, but this time we were subtracting negatives, so we're adding now. We can actually add this 40.3 at the end, add 40.3. So do the math there right. And you should come out with, do it. Negative 1124, negative 1124 kilojoules per mole is my delta H of that reaction. So what does that mean? Once again, it means we have an exothermic reaction and we're giving off a lot of heat. We are doing a combustion reaction. Combustion reactions give off heat, so we expect them to be exothermic. Not as much as the hydrocarbon we had, but we are getting a combustion reaction, so we are producing a decent amount of heat out of that. All right, so that is the standard way of doing a heat of reaction. And that heat of reaction for number 2 is now complete. All right, we'll stop this video here and keep it relatively short so it uploads a little quicker. Then we'll jump into problem 3 right